Yeah, so good evening. Uh, Good evening. Welcome to this electrical measurement and electronic instruments course, week 10. Today, I might keep this session short, but yeah, we'll go through the assignment questions, how we can solve that, and I'll just check if my voice is clear. So, we'll go through that assignment questions, which will help you in solving your this week assignments. And I think this is now the third last session, and next week that will be last session, that is week 12 session. Then we will be winding all the things, and next week we'll be having the second last session. So if you're seeing this live, or like when you see this in YouTube, then just go through all the YouTube lectures sessions, because your exams will be nearby, and you can ask your doubts, you can collect your doubts by, and you can then ask in discussion forum, or like you can ask in this in the upcoming two live sessions also, or maybe if you join in this, then also you can like go for like asking your doubts. So so yeah, so we'll start with this, with some of the previous year assignment questions that may help you in solving this week's assignment. So I think in this week you have been taught about this instrumentations with op amps, like instrumentation amplifiers, and how you will realize that using operational amplifiers, and maybe why you need that, why we need electronic instruments, and then this one, then like different applications of instrumentation amplifier. So basically, uh, so we are using this instrumentation amplifier as we are like avoiding this loading effect, which we see if we use a differential amplifier, like connection in differential configuration. Then we might like face this loading effect of ours in our system. But like instrument amplifiers, as you can see in front of you, like this is one instrument amplifier, so there will be no current passing in these branches, so like it helps to avoid, like it helps to give lot of improvement in your applications. So that is one thing. I'll just wait for 1 second. Please. Just came to see okay. Yeah, yes, yeah, it's fine. This guy moved here. Yeah, it was moved there. It's the NPT realization. Yeah, from 6 to here. Here. Can be over. Yeah. Sorry for the delay. Yeah. So now we are back. So yeah, so we are talking about this instrumentation amplifier. So then we can see that. So let's talk about the first question. So first question says that uh, consider the above instrumentation amplifier circuit, where I is so this is the I. So we have to calculate this I in milliamperes. So I think if you know the basics of operational amplifiers, the virtual short concept, and how the input size of this op amps terminal works, then we can say that we can easily solve this. So in this question, like we need to find I. So I think it's simple. Like if we consider this to be zero point 0.1 volts, I'll just erase this thing. So by the way, is there any disturbance when I'm speaking? If you have any disturbance, then you can say or if there's no disturbance, then you can say something. You can reply on chat, because I have to be make sure like. whether it is fine or not. Can you reply on chat whether it is fine, my voice? Okay, thanks. Thanks. So now, so we have this. So let's consider zero point 0.1 volt here. So we are taking this as reference. So we are taking this terminal as reference terminal. Then we have zero point 0.1 volt here. So by virtual short, as you know that this is a negative feedback. By virtual short, we can say that this is zero point 0.1 volts here. And then at this is 0 volts, then this is 0, so virtual short again, so this voltage get transfers here because this is again a negative feedback amplifier. And then we have C as 0 volts. Now they are asking for this current, so now we have these two voltages, we can find current easily. I will be what? I will be 0.1 by 2 kilo ohm resistor is there, so 2 kilo ohm, yeah, so it will be 0.1, yes, 0.05 milliampere. Okay. I think this was straightforward. This question is straightforward. Then the next question, it says that what is the VAB voltage. So just to be just to clear this fact that this they are talking about this voltage, not this voltage. So they are not talking about this VAB. It's some like typo, so we would have like placed this with some another name or something. But anyway, they are talking about this VAB. Okay, so this VAB is the drop across this whole AD branch, I will say. This whole AD branch. Okay, so now this thing, so we have 0.1 volt here. So we know the drop across this branch. This is 0, and one common thing in the all three parts of this branch is that the current is constant in that. So like this is the I, so because no current will be flowing in this input terminals of the branch of these operation amplifiers, so we can say the I is flowing, the same I which is here, this I is flowing from this above this branch, then it is flowing this here also, and it's flowing here also. So the current is constant in this whole branch. It is not going inside the input on inverting terminal of the operational amplifier. So keeping that in mind, so if we say that what is the, if we find the voltage, so I will just denote this something with, I will say E, just to avoid confusion. Instead of B, this is E. Okay. So VAE will be, so the whole voltage basically will be VAE plus VEC plus VCD, that is equals to VAB. Okay. So what is VAE? Then it's, I think, straightforward. Resistor into I, that is 0.05 milli, plus VEC is 0.1, that we already know, that 0.1, this 0.1 voltage drop is there, that we know. VCD will be 2 kilo into I, so I will be 0.05 milli. Okay. 0.0 milli, so we will get VAB. So VAB we will get VAB as VAB will be equal to if we calculate, so I have calculated that, so that will be 0.3 volts. Okay, so it's I think straightforward. Like you just have to keep this thing in mind that this I current is constant. This I current throughout this branch is constant, and then keeping using that fact, then you can like solve this thing. Now the proper sign, so it's positive 0.3 volts. It's fine. So now the next question, they are asking about the V0 voltage in volts. So what will be V0? So let's see. So V0 is this. So if we let's say if we like separate this stuff, because we already know VAB, let's separate this out and only consider this part of this amplifier. So what we have two resistors differentially connected. So we have two resistors differentially connected to this op-amp, here minus plus, here plus, here minus plus, here 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 plus and it is 8K, and it is then 8K, and we have 2K, 2K, we have V naught here. So now this voltage, that is VAB, we have 0.3 volts. We just calculated that. Now again, what we can do, we can consider this to be 0.3 volts. This can be the reference ground. So now just look at this part. So this is what, this is ground, this is ground. So this will be 0 volts because no current will flow in this branch, and since there is no voltage drop, so there will be no current here, no current here, no current here. So we will have 0 volts here, okay, at this terminal, at the non-inverting side of the operational amplifier. Now this, because of this virtual short, and why virtual short is there, because of this negative feedback, we'll have 0 volts here. Okay, so now I think it's straightforward. So we have 0.30 here. So what will be the current? So you can, current will be 0.3 by 2K, and that same current, this same current I is flowing through this branch, the feedback of this operational amplifier. So using that, but it will be negative because this is 0 volts. So V naught will be 4 is a 1.2 minus 1.2 volts. Okay, so what we did, so we like initially, so this was the configuration of instrumentation amplifier. So then we took the advantage of the fact that the current is constant in this whole branch A to D. Then we calculated this the voltage drop across this, voltage drop of VAB. Then we separated this part just to make things easier for us. Then we took this part only, and then we calculated the V naught voltage out there. So this is okay, this is also fine, and this also will done. Okay, now the next question. So now we can see there is a diode there. So if a diode is there, so we should like keep this thing in mind, that it may allow certain, it can only, it may allow certain I will say certain polarity of voltage across it. So so if you I will just, so I think you know this, but still I'm just telling it that again. So if there is a sinusoidal voltage being inputted to this diode, then what we have, so we have like, we will get a rectified, half rectified output, because at the positive side, in the positive cycle of this input, the sinusoidal wave, it will output, it will give this output, because it will be acting as a forward, it will be acting in its forward bias zone. But in negative zone, it will be 0, because it will act as an uh, open circuit element. So now in this we have to keep this thing in mind, and let's see what is happening at the output of this uh, operation amplifier. So we have a pure sinusoidal wave. So let's say, so we have this negative feedback, that is important to check. Once we have that, then this V voltage can be transferred to this side way, okay, because of virtual short concept. Now you see that when this was, so V in, like let's say V in was like this, it was like this sinusoidal voltage. So when this was positive, so when you have to check a state of any diode in a circuit, what you do, so you simply check its anode and cathode voltage, like in a way that, so let's say V in is there, so forget about if there is any current or something like that, just say that okay, V in, that like some positive voltage is being there at this this cathode anode side of this diode, and that is for the first cycle, it is positive. That means wait, yeah, so that means like this side is positive with respect to this side, okay. Or you can like analyze this any diode circuit in an operational amplifier by the fact that yeah, I think this is the better way to do this. So we had this V in voltage, so this was the positive this is the positive cycle of that. So it came here, so we can see that this made this reverse bias. So that's why like it will be like off, but in negative cycle, uh, but I think it will be on in positive cycle. Yeah, let's analyze this in this way, in this manner. So if so, one thing to keep in mind is if the diode is on, then this feedback will work. If the diode is off, then this feedback will not work. The answer to this reasoning is that when you are like when this diode is on, then only this op amp will give a feedback. Then only this thing is being attached to the feedback and getting given back to the op amp. But instead of that, but if this is not open, if this is open circuit, this diode, then what happens, it is not able to transfer its output to this side, like let's say here. So this feedback is hanging, so this feedback is floating. So if this feedback is floating, that means its feedback is not, so it is not acting as that feedback circuit for this operational amplifier. That means we cannot use that virtual short concept, because if you recall your lectures, virtual short concept only works when there is an output, certain output for this op amp. Yeah, it's true, like if so this was, if this was the open circuit thing, if the feedback was being given from this part, then it is fine, but we are giving feedback from this part like this. Okay, that's why this feedback will not work in that case if this diode is open. Keeping that thing in mind, now we will analyze what is happening in this circuit. So let's say, so first of all, this op amp will act as a comparator. So when, because we don't know whether feedback is there or not, that will depend on diode's position. So we gave this sinusoidal voltage. So this was positive, this was negative. So this was positive, and if this is a comparator, then we can say this is grounded, because this branch is meaningless. So this is grounded, so this is 0 volts. So definitely in positive cycle we will have output as saturated output, so that will be plus 15 volts. Okay, so that is this side of this diode. That means the at the positive cycle the output will be there, some sinusoidal output of this op amp. So this is V naught. So some sinusoidal output of this operational amplifier will be there. Then in the next cycle, that is in the negative cycle, what happens that so this is negative, so this is negative, and that means like this will be, instead of 15 volts, this will be minus 15 volts. Initially the this operational amplifier is acting as a comparator. Okay, if we don't know, if because we don't know whether feedback is there. So since this is negative, so this will become what, this will become off. So if this is off, then there is no feedback, that means there is no voltage. So this ground is being fed to this PMMC meter, so that means we don't have any feedback at that point. So basically this whole circuit also acts as a precision, this we say rectifier, and sometimes we say precision rectifier. Why we say precision rectifier? Because if you will normally use diodes without any operational amplifier, then there is a limitation in diodes that they have this reverse bias voltage at like 0.7 volts or 0.5 volts, which makes which gives us a constraint that we cannot use signals below their for reverse bias voltage. Let's say we cannot use signals below their 0.7 volts for a silicon diode, and similarly 0.3 volts for a germanium diode. Okay, so but if we use this operational amplifier, we are getting a precision rectifier. So how is the small signal is, smaller the signal is, it will not matter. It will give a half rectified output. So this is a precision half wave rectifier. Now moving forward, so we have, so they have given this reads 1 volt PMMC voltmeter. This reads we have 1 volt, and we know that PMMC meter only reads the average output. It considers the average of the, like whatever it's being inputted to it, the meter. But we have to calculate the RMS value of the input signal V in. Okay. So what we will do, just wait. Yeah, so we need this voltage. So this is what V naught, the PMC voltage is. So it will be, so V naught, that is this voltage V naught is equals to what? Now again consider, so there was some current flowing, and that current will be same in both the branch, both the resistors, here in this resistor and in this resistor. Okay, and we need this voltage V in. So what will be V in? V in will be, so it is basically, so we can reduce this as, this is this branch, this V in voltage here, this is ground, and then we have this V naught voltage across this branch, and this is 7k, this is 1k. So what will be V in? V in will be V naught into simple voltage divider rule we can apply, 1k 1k plus 7k. Now our next step is to calculate V naught. V naught is what? So V naught is an average output of a PMC meter. Basically, it's the output of PMC meter, and PMC meter gives average. So it is, and since this is half rectified output, that means its average will be, so V naught is what? Average value, and it's for a sinusoidal wave. What is the average value of that sinusoidal wave? It is Vm by pi. For a full sinusoidal wave, it is 2 Vm by pi. So if you have followed my live session, so in one of the sessions I have mentioned, for all the basic signals like sinusoidal, triangular, seesaw, all those square waves also, the their RMS average values, like what are the formulas. So I think you should keep that thing in mind, so that it will help you in your, like, solving these questions. So V naught is this Vm by pi. So we can calculate. So Vm is basically the peak voltage of this voltage, this signal. So we have V naught into pi equals to Vm. But now we need the RMS value. So what will be the RMS? It is Vm by root 2. So it will be V naught pi by root 2. Vm. So this is Vm. Like if we are going for this RMS value, so this will be equals to Vm by root 2. So this is the RMS value of the output signal, Vm by root 2. So we have V naught pi by root 2. Oh shit. Wait. Uh, I think I'll have to. This happened last time also. I'll have to just come back from this. Wait. Just wait. Just now I will start. Yeah, now it's fine. So we were talking about, so we got the RMS value of the output, so that is V naught pi by root 2. And we needed what? The RMS value of this input. So this is the input. What will be its RMS? So V naught RMS 1k by 8k. This same expression I have used here. Okay. So this was generalized expression. If we have to calculate the RMS of this V input, then this will be in RMS and V naught will be in RMS. If it is average, then if this is V input, they are calculating for average output, for average value of this V input, then V naught will be in average. We will take the average of V naught. So using this thing, so we have this VRMS of output, that is V naught pi by root 2 1 by 8. So if you solve this, then you will get, so V naught is basically 1 volt. So they mentioned that the voltmeter reads 1 volt. Okay, so this was the average 1 volt. So this value is V naught average. I think it became a little clumsy, but yeah. So if you are following, so it's fine. So this is V naught. So this is V naught average. So this will be 1 into pi by 8 root 2. So you will get around, yeah, so you can solve this further. It's fine. Okay. So again, if we go, so what we did, so we had this diode, we checked whether it will be on, it will be, or it will be off. So in the positive cycle, what happens, like this diode, this initially this operational amplifier will be acting as comparator. So we'll get a positive saturation there that will make this diode on. So in that positive cycle we get this output as the same as that, not the same, but kind of similar as that of input. But in the negative cycle of the input, then this diode is off. That means that there is no feedback for this operational amplifier. That means we have zero output. Okay. Keeping that in mind, this PMMC meter, what does it do? It calculates the average value. So if it calculates the average value of its voltage, then we have this formula. And why we use Vm by pi, not 2 Vm by pi? Because this is a half wave rectifier. Okay, that's why we use this formula. Using this, so this is V naught average. Just keep that in mind. We can calculate the peak value of the signal. So this is Vm. This is Vm. Okay, I have mentioned here. So this is Vm. So Vm we calculated. Now if we know Vm, so we can calculate the RMS value of this signal. That is what? I'll write that down again. RMS value of this signal is, it is equals to Vm by root 2. So now we know Vm, that is V naught by pi. So it will be V naught, or V naught is what? V naught average into pi by root 2. That is RMS value of the signal. So that's what we did here. And after doing this, we got this V in expression, that is V naught into, using the simple voltage divider rule in this branch, we got V naught into 1k by 1k by 7k. Okay, so that is to drop across this 1k resistor, this resistor, 1 kilo ohm resistor. So thus we have that, we have V in expression, we have V naught. So V naught RMS is basically V naught pi by root 2, that also we got. Then we can finally like calculate the V naught average. That's what they asked us. Sorry, V naught RMS we can do. V naught RMS. Okay. So I think I will connect my PC with some another this Wi-Fi. So just wait for it. But this Wi-Fi is slow. Just wait. Okay, it's now from how it change. But anyway, so yeah, we have this RMS value for this. This is the RMS value. V in RMS. We calculate that. Now the next question. Moving to the next question, that fifth question. So it is saying that in the above electronic voltmeter circuit. So this is a voltmeter circuit. This yellow color box. The full scale deflection current of the PMC meter is 10 milliamperes and its coil impedance is 600 ohms. The forward voltage drop of the diode is 0.7 volts. So there is, in this diodes there are 0.7 volts. So then we have to calculate the RMS value of the input voltage V in this one, that would yield the full scale deflection. So then when they ask for us full scale deflection, then we know one thing, that there is a current of 10 milliamperes, because it is being given, it's being thrown through this diagram. So let's say if we talk about positive cycle of this V input, so this was some sinusoidal. So positive cycle, then the current will go like this. For negative cycle, the current will go like this. Okay, so these are two current paths, but we will get the output. So earlier what we saw a half wave precision rectifier. So this is a full wave rectifier, full wave precision rectifier. So the output we will, so input is like this, output we will get as like this. Okay, now they are asking us to calculate that RMS value. So we also know that 10 milliampere is the current. So since there is no current in this input inverting terminal of this operational amplifier, so we know that I will be from here, and that I, if that is the like the positive cycle, then I will go from here, otherwise I will go from here. Okay, depends on which cycle we are talking. So let's say for positive cycle I is like that. So what will be V in? V in will be 10k into I. But now one thing to keep in mind is that, so this is what, this is the average value. Okay, so this is what V in average. Because, why is this mean average? Because PMC meters, what they calculate the average value of this. So they calculate whatever we being fed, so the average value of that value, input value. So current is the full scale deflection which we are talking about, that is an average value. So we will get 100 kilo 1 milli, so it will be 100, yeah, so 100 volts. But this is, keep in mind that this is V in average, but we need RMS value. So again, what is the sinusoidal waves average value? That is 2 Vm by pi. So Vm is what? Again the peak value of this V input. This was V out. Okay. So this is again this expression. That is the average value. So Vm we can calculate from here, 100 pi by 2. Okay. So this is 100 pi by 2. Now since we got the peak value of our input voltage, so it's easy to calculate the RMS value. So what is RMS of input? It will be Vm by root 2. Since we know Vm, we can calculate this easily, that is 2 root 100 pi by 2 root 2. Okay, so yeah, so I think in these kind of questions, what your motive should be, like to calculate somehow to get to this peak value of that signal. So whether we are calculating RMS or we are calculating average of a signal, there this the knowledge or the information of the peak value, peak voltage is there in that signal. Okay, so if somehow you can find that from either the average value or the RMS value, so you can then calculate the other things from that. So calculating the peak value is the key, like this. So yeah, we are done. So this was the RMS of input. Then the next part, so the sixth question, because this is the question for, yeah, so just say the extended question. So they are saying estimate the RMS value. Again, they are saying estimate the RMS value. The input voltage V in if the meter shows 65% deflection. So instead of 10 milliamperes, it is like 65% deflecting. So that means 0.65 of the full scale deflection current. So initially full IFS was for 10 milliampere. Then I full scale at 65% will be equals to 0.65 into 10 milli, that will be 6.5 milliamp. So now if you observe this VRMS, so what is VRMS? VRMS is directly proportional to Vm, that is the peak value of this sinusoidal signal. Also Vm is what? Vm, this Vm, which is this formula, it is also directly proportional to the I average. And I average is what here? It is the deflection in the PMC meter. That is basically the current in the PMC meter. So now if we have 0.65 of that current, that is 6.5 milliampere. So the new RMS value, let's say dash input, is directly proportional to, we can say it is directly proportional to the scale deflection, because this is this, and Vm is this, which is this, and which is this. Okay, so it will be VRMS prime divided by, or I'll say VRMS prime. Yeah, okay, VRMS, that was initial VRMS. It is also directly proportional to the current, that is I full scale, and this is 0.65 of I full scale. So we will get new RMS voltage to be 0.65, because this will get cancelled, into VRMS, the old VRMS, that is 0.65 into this value, 100 pi by 2 root 2. Fine. Just go to this. So this is how we calculated this RMS value. That's great. I'll just disconnect this Wi-Fi so that just wait for a while. Just wait. So I can connect to the faster Wi-Fi, higher speed Wi-Fi. Yeah, it may, the connection may got lost, but just don't worry, I'll come back. Hello, yeah. Yeah, now sorry for the delay. Now I think I'm connected with a better Wi-Fi. Yeah. So this is also fine now. There will be less lag. Otherwise, there was an issue. Okay. So yeah. So we can just calculate the RMS value. Now moving to the, so with the 65% deflection. Now moving to the next part. So estimate the input resistance of the electronic voltmeter circuit. So whenever you face any question saying input resistance, just keep in mind you have to calculate the input voltage of that whole system and the input current being fed to that system. Don't think too complex, like okay, we have to calculate the Thevenin or something like that. It can be easy also. So like in this estimate the input resistance of electronic. So electronic voltmeter circuit, say this is the yellow box. We know V input, we know I, so this is I input. So what can be Z input? Z input is V input by I input. And another thing, so if you are considering this as RMS, let's say V input is RMS, then I input should also be RMS. Okay, keep this thing on in mind also. Like Z is not, the impedance value is not having any RMS or some average value. It does not make any sense. Okay, so like even in other subjects also in electrical, like if you are considering RMS, you consider RMS for each and every part of that system. So if this is RMS, this is RMS I. But if B in is average, then I in will also be the average. Okay, so this thing to keep in mind. Then then so we will go for this average value. So B in average was what? we just initially we calculated. So we had, where it is, so this is V in average, okay, that was 100. So we have 100, and if we are talking about that input impedance, and that will obviously be decided based on the maximum current deflection. So this is 100, this is I input, that will be 10k, so it will be 10 milli ohms, 10 milli ohms, okay, sorry, this is 10 milli, now current is 10 milliampere, so this is 10 kilo ohms. Okay, so this is the Z input. Now the next question. So this question is estimate. Okay, yeah, this is done. So the next question is consider the above electronic ammeter circuit. So again, this yellow box is the electronic ammeter circuit, and then we have this estimate the input current I in when the PMC voltmeter reads 9.1 volts. So this is reading 9.1 volts. So if it is a PMC instrument, that means this is the average value. Hmm. And what is this voltage? This voltage across this branch. And we need to calculate the I input, that is I in this one. So what we will do? So I input. So basically, I input is going from this. That we all know, because there will be no current there. And if I in is flowing out from this, so then the voltage drop across this branch, it will be 8 into I in. If we consider this as reference, that is ground. Okay, so this is 8 into I in, that is the current being given, and that is the voltage drop. So if this is 8 in, just also think of that this is a negative feedback operation amplifier configuration. So we can use that virtual short concept here. So this will also be what, 8 in. So this will be what, 8 in. Now the full voltage drop will be what? It will be 8 input into 2k. Sorry. So this is the voltage drop, 8 input. 8 input plus 8 input into. So current will be what? Current will be 8 input by 2k. This is the current flowing like this, and that will be the same current flowing from 98 kilo ohms, because there will be no current in this branch. So into this will be 98 kilo, which is equal to negative of V naught, because if we are like we know it's I think positive 8 in, yeah, because current is flowing downward, so it's positive. So V naught equals to 8 input plus 2 4, so this will be 98k. So yeah, so we'll just instead of 2 4 432 382k I in, and this was 8 in, like 8k I in, not 8k, it was only 8. Correct. Oh sorry, this k is being cancelled, so this will be 382 I in. So this will be what? This will be 390 I in put. If this is 390, then we have. So this is what V naught average, and they are asking the input current I in. So I in will be what? We know V naught average is 9.1 divided by 390 will be I in. Okay. So if you solve this, you will get the I input current in milliamperes. This is fine. Then the next question is estimate the input resistance of the electronic ammeter circuit. So again for input, what we have, V input by I input is Z input. That means V input was what? This 8 input voltage. I 8 in. So I in is I in. Z input. So if we cancel that, so we'll get 8 ohm basically for the Z input. Okay. So this is the thing. Estimate. So this is also done. Now the next question. So they have used PMC meter in the feedback, and sir, can you explain it question again? Okay. Question 8. Okay, I will explain this in another different page, new page. Here I will explain. That page is alright. So just let me draw the diagram. So this is question 8 assignment. This. So there is one input current I in. It is having 8 ohm resistor. Then we have this plus minus. Then we have 98 kilo ohm resistor here. We have 2 kilo ohm resistor here, and so this I input is going back from this side. We have one PMMC meter attached at the output, and V0 is this voltage plus minus. So the first question was this. So consider the above electronic ammeter circuit. Estimate the input current I in when the PMC meter reads 9.1 volts. So this is reading 9.1 volts. 9.1 volts, and we have to calculate I in at that moment. So we can, what we can do, so I in is the current flowing through this 8 ohm resistor because it will not flow from this branch then, and it is being fed back there. So we can say what is the voltage drop across this branch. What is it? It is I in into 8 or 8 I in. 8 I in. If we are taking this as reference, or we are taking that as ground. So this whole branch will be ground. Okay. If we are taking that as 0 volts, then obviously all the drop is across this point. So now, since we have a negative feedback system, we can say that this 8 in voltage is being transferred here due to virtual short. 8 in. So it came here. 8 into 8. Now we know that this PMMC instrument is having 9.1 voltage, minus 9.1 volt. Sorry, 9.1 voltage. So this is basically what average. If we know this voltage drop, I'll say. So if this voltage drop we know, then we can equate that with the 9.1 volt average value. So 9.1 is equals to what? So now consider, let's say this is I, this is I, because it will be same current, no current will be flowing into the branch. Okay. So this is I, this is I. 9.1 will be what? 98 kilo into I plus 2k into I. And what is I? If we look at this branch, uh, if we see at this branch, I equals to 8 in, 8 in was the voltage. This 8 in was the voltage being dropped here due to virtual short at this point. So I will be 8 in by 2k. Fine. So we know this will be 100k, and I will be 8 by 2 I in k. So k cancelled, 400 I in 9.1. So this whatever we'll get average, because this is average. That just keep that in mind. So 9.1 by 400 equals to I in average. Now in question, they haven't mentioned whether to calculate the RMS or average. So if that is the case, then go for RMS. Because in all other questions they have specifically mentioned that they need RMS value, but here they haven't mentioned. So it's average only. So this is the average. 9.1. So this will come out close to as 22.75 billion. Okay. Yeah. So this was there, and the next question in this was estimate the input resistance. So if we are looking for input resistance, I again mentioned that for Z input, that is the input voltage divided by the input current. Okay. So this is basically input voltage. V input. This is input voltage. And if we are taking this as reference, that is 0, then what is V input? That is the voltage drop across this, that is the 8 in. That is the voltage drop across this 8 in. So this will be 8 input, 8 in divided by I in. We can keep it as I in. So this is I in. That is the current which is being entered to this whole system. This whole system. So it will be 8 ohms. Okay, so this is the explanation for this. If you still have doubts, you can ask me again. Otherwise, we will go towards the next question. Then just go through like what I told you. Just take some minutes. Because your final exams are, I think final exams are coming maybe after 2 weeks, so you should now really like extra like practice and like take this live session seriously. Just let me know if you have any other doubts. So if no, then you can ask me whenever you want. So the next question, the 10th question. Here we have this diode in the feedback and even the PMC meter in the feedback. And they are asking in the above electronic voltmeter circuit. So this is a voltmeter circuit, and final exam is subjective or objective based. That I think only professor can tell. He only can tell. But I think it will not be subjective. It will be, I think, this MCQ based and then numerical. So numericals will be there definitely. Yeah. So numericals will be there, and I think this MCQs will be there. There can be multiple correct questions. That so it's just like the pattern of normal gate exam, but not the level of gate exam. Pattern I will say, because there are no subject questions, only the objective questions, and then numerical based. So if the person, the people who, I think you are already doing these, all are numerical based only. There are hardly true false questions. So and there will be this like questions on which like 4 or 5 questions are dependent on. So if you do mistake or commit mistake in the first question itself, then your all the 4 or 5 questions will be gone. So I will just say like be focused while reading the question, at least reading the question, read that question properly 2 3 times, then only go for attempting the question. And because if you just make the first question incorrect, then it will be like that whole 4 or 5 questions will be gone. So just keep that thing in mind. And I think science, there will be some normal basic calculator in the window itself for normally these NPTEL exams they have. It will, I think, definitely it will not be scientific, but you can use simple cosines and tangents, that those things, but not that proper scientific calculation. It will be in the window itself. So yeah, these are the normal basic things which normally the NPTEL exams are. But I will say, like focus on assignment questions. These are really important for your exams. And like if a professor has like given some, let's say he has given, okay, try this yourself, like, or say he said, okay, let's this is the homework for you, and there is nothing discussed in the next class based on that topics, then it can come. So there are high chances that these type of questions will come, because the questions which are being given homework, homeworks for you in the lectures. I'm talking about the lectures, and definitely assignment question. Those you should practice all those questions again and again, and obviously like the questions, extra questions which I give, that will give you more depth to that you are understanding it out. But don't go like see what I teach you. If you find like this question is like not what we have been taught, is not like overlapping that concept, then you can skip that. I like gave only the extra knowledge in many of my questions, just so that you have better understanding and better visualization of what is going on in electronic instrumentation. But anyway, there were very good questions also, which will help you in your exams. And so assignment questions are important. Look for like see all the lectures properly. If sir has given any things in between the lectures, like this is a homework or just try on your own, then look for that. He might give some question based on that. So it can be like this. Okay. But the questions will be numerical and MCQ based, not subject. I think so. But again, you can ask in the discussion forum. We may reply. So just for the sure. So yeah, so this question 10. So question 10 is like so there is a diode there. PMC meter is there. So PMC meter is having now 200 ohm resistor. The forward voltage drop of the diode is, so this is having 0.65 volt forward voltage drop. Estimate the RMS value of the input voltage V in if the PMC meter reads 8 milliampere. So when they say PMC meter reads 8 milliampere, there are two things. One thing is that this is average value. Second thing is that is the current flowing through this feedback or through this is 8 milli. So this will be also 8 milli, and this will be also 8 milli. When this diode obviously it's in forward biased. Forward biased. So now they are asking us to calculate V input. Okay. So let's calculate the V in average. So one more thing you have to keep in mind, like so V, let's say V involves this, a sinusoidal voltage, complete sinusoidal voltage. This is V in, this is Vm. What will be the output? Output will be what? So for a positive cycle, this diode will be on. Okay, it will be forward biased because current flow negative, so it will be forward. Then so that in that case we will have some V naught. But in negative side, in negative, so when this will be V will be negative, so this will be what, reverse bias, so we will have nothing. So in that case, what we are getting a half wave rectifier signal, half wave rectifier output. Okay. So if this is a half wave rectified output, that means whatever average value we will be calculating, that will be based on the half wave sinusoidal signal. So just keep that thing in mind. So you have to see whether the circuit is a full wave or half wave. Based on that, you have to choose your formulas. So this V input. So let's calculate. So the 8 milliampere is obviously average value of that current. So what we can do, so we can do this V in, we know V in, so this is 0 volts because of virtual short, this is ground. Okay, so V in by 40 equals to what, the current flowing through this branch, and that is the deflection current of the EMC meter in the 8 meter. But this is what average, so what we are calculating here, so this is also average, simple, no confusion. Then V in average will be equal to 8 milli into 40. You will get 20 milli, that means 0.32 volts. And this is now average value. Now when you are using the formula, that is, I should use to Vm by pi or Vm by pi. So for sinusoidal there are two. This is for half wave rectified sinusoidal wave. This is for full wave rectified. So we will not use this because we already said that this is a half wave rectifier output. That means the output is based on half wave rectified signal. That means this current is only for half wave of that signal. That's why we are taking this formula of that sinusoidal signal. So V in average can also be written as Vm by pi for half wave rectified signal, which is equals to 0.22 volts. So here from here we got the peak value of that sinusoidal signal 0.32 into 5. This is peak. Now if we have the peak, so they are asking for RMS value of the input voltage. So we can then easily get it. So V in RMS now it will be equal to 0.325 divided by simple root 2. That simply is peak value divided by, sorry, not by 2. So this is the RMS value for a sinusoidal signal, and this was the average. So this thing also have to keep in mind that half wave rectified. Okay, half wave rectified. This half wave rectified given by root 2. Okay, half wave rectified sinusoidal signal is having not Vm by root 2. I think it's Vm by 2. Let me check. Let me check. Just if you know, you can also tell me. Let me check. It's Vm by 2. Yeah, it's Vm by 2. Sorry for this. So this is Vm by 2 for a half wave rectifier. So this will be Vm by 2. Okay, so this will be 0.32 pi by 2 and 0.1126 something into 3.14. You can calculate that. So this is the thing. Now the next question. Estimate the maximum input voltage that can be measured before op-amp saturation creates problem. I'll just wait for a second. Okay, so yeah, so the next question is estimate the maximum input voltage. So maximum input voltage will be when the output is what? Output is 15 volts or minus 15 volts. But it will be 15 volts because it is only working in positive cycle. So it will be 15 volts. So what we can do in that case, we need to find the input voltage, RMS input voltage. So we know for this branch, it is so we don't know the current in that case when the output is in saturation. We'll first calculate that current. So how about it will be 0.65 voltage is the voltage drop across the diode in forward region. Then we have 200 is the input, is the internal resistance of PMMC meter. Then we have 200 into I, the current through that PMMC meter, equals to what? V output. So this is the current through this PMC meter, 200 into I, and then we have 15 volts. So this is basically the maximum saturation voltage which we can get for this for this system. So we can calculate I from here. So this I will be 15 minus 0.65 by 200. Okay, and this is what? This is I average. Now if we have this thing, then V in average will be equal to this I average into what? We have 40 ohms, so current I in average is going from this I average basically. So it will be multiplied by the resistance. So this thing will be given here and multiply 40. So we'll get the average value. Now if we have the average value, that what does that mean? That is Vm by pi. So we will get Vm from there. Vm will be I average into 40 into pi. From this, what we can do? We can calculate the RMS. That will be Vm by 2 for a half wave rectifier circuit. 45 into I average divided by 2. So we'll get the RMS value. VRMS. Okay. Of input. So this was about this assignments. This is the assignment questions. So today I will keep the class for the assignment discussion only. So if you have any doubts related to the assignment, then you can ask me. Uh, you can think, you can take time. I'm here only. So yeah. Otherwise, then I think it's fine for today. In next session, so what we will do in next session? Anyway, we will solve the assignment questions for the next, which will help you for the next questions for the next assignment. But then at the same time, I will, or you can come up with your assignment like previous till week 11. All the assignments questions, if you are having doubt in when you're having a single doubt in any of the assignment question, then we can discuss that. And then I will come up with some extra questions which will not be unnecessarily difficult. It will be such like it may come in this your exams, or it will be related to like what we have studied in this session, in this lecture series of your course. That may be helpful. So that will be like yeah, kind of simple based on these course material, course study. So by the way, yeah, if you have any doubts, just ask me. You can chat. You can write in the chat. So now the session is open for discussion if you want. We will not
Sir,
solve any. Yes, yes.
sir, in op amp, that
Yeah.
offset voltage, sir,
Huh.
that session you discussed R1 parallel with R2, sir, with that will be connected to non-inverting terminal, sir. That
Mm-hmm.
you discussed, sir. Here, if some other value if we put means, how will that get that it will remove that offset voltage, sir?
So you are saying, wait, I'll add one quick. So you are saying when we have some op amp and we have to remove the offset voltage. So we connect something here. This you are saying? This is
Yes,
R1
sir.
parallel to R2.
But bias current must be zero now.
Yeah. So this compensation, I think this is for bias current compensation. So when we use this, when I said this is for like offset correction. So this is not for offset correction. This is for bias current compensation. When we use R1 parallel to R2, we are removing the effect of IB, the bias current which is here, which is being also coming from the feedback. For offset, what we do, like yeah, for offset correction, so we will have this terminals open for this operational amplifier. So let's say this is, there is no voltage being given to this, and then if we are getting some voltage, then what we do, then we use some potential meter. So there is a pot being attached somewhere like this. Then we change that system so that this V naught becomes zero when we are giving no voltage to this input side of this operational amplifier. And then we change this yeah, I think this potentiometer is connected in the input side of this operational amplifier, and then we change the voltage of that potential meter so that this output becomes zero. That's how, that is the simplest way of removing that offset voltage. But I think I didn't share this thing in this session. Maybe I did this in my previous Neptel sessions. That
Yes,
was
sir.
offered.
I was seeing that, sir.
Oh, okay, okay. Yeah, I think yeah, it's yeah, okay. Yeah, maybe in the starting of this year. Yeah. So can you tell me the video exact? Do you know the video, YouTube video which I was discussing?
I have to see, sir. Sir,
Ah,
once
okay.
again, sir. Another one.
Yeah.
Comp mode reduction ratio, sir.
Ah.
Uh, uh, why CMRR deteriorates in op amp, sir? Because when why it actually why what makes CMRR to reduce, sir?
So it's like. When we see, so normally op amp is not something like So if you see inside the op amp, what is there? Like there's so many BJTs, so many transistors like MOSFET, JFETs. If we talk about FET transistors, so what happens when you are like increasing the frequency? Huh. So what is happening? So these transistors will behave differently in this high frequencies. So if we go much more deeper, although I have not that much clarity, like what exactly happens in their this bias regions and their forward bias region, saturation region of this JFETs and all. But I think just for a vague idea, like we had this MOSFET structure like this. So if you are increasing the frequency, then there will be something, some exceptional behavior of this transistors happening. So that's why like like it is not able to properly behave if you are exceeding the frequency. Because what CMRR graph is, it's like this something. Okay, this is frequency. So this frequency is the culprit. So like if you are increasing the frequency, so then we don't have the control of these electrons, and we cannot say okay the controls were the electrons were at the like exactly were traveling in the way we wanted. So there are lots of phenomena going on. That's why it's like it's more of like a materials question, like why it is dropping like that. I would say manufacturing question basically.
Okay, sir.
Yeah. I may have to revive. I may have to see those videos again because I it's been a while. Maybe next session, next NPTL session of January, I may take that course again. So I may see some of you there. That's all. Yeah. Any other notes apart based on this this thing, this session, this lecture, this course? Ask me. I will give a proper answer next class. ICMRR, factoriates. Sorry for the spelling. Factoriates when we increase. I hope it is in manufacturing side of that. But I will. I hope I find something good explanation. Why ICMRR deteriorates when we increase the frequency. Yeah. Any other questions? Just ask me. So I think about based on exams, although everything is important, but I may say that the questions on this ammeter voltmeter, they definitely some questions will come from that. What I feel like. Then obviously operational amplifiers, you will get one or two questions, but I think those are somewhat like these. Those are easy only operational amplifiers. Then we had I will say what other so from this topics yeah. So wattmeter I went into three-phase system and all some derivation, but you should only focus on like what he told, so that is good for exams. Then let me see. So you have been through okay. So there can be one question from this AC bridges, like where you have to like balance the beats on which condition, and you have to solve for the answer, final answer. That can be one question. That is a typical measurement question. Then voltmeter emitter, like variations in that, increasing the ranges of voltmeter or emitter, their different configurations, and even the loading of them. That definitely some questions will be there on that. What I have faced in my bachelor's and all. What I feel like. So that can be there, and then what you study. Yeah, bit circuits. One question can be from that. Then, although everything is important, I'm not saying that those are the important things, but still, one will be there from watt meter. I'm sure about that. Then single phase unit, no, not from there. You may, I don't know, but yeah, from these different moving coils and all those. Now you did that initially. From there you can get the, like, you should know the torque equation and you should know how to balance that. And because there are different torque equations for each and every, so was each and every meter, so that you should keep those things in your mind. And then there can be this full wave rectifier questions based on PMC meter. Those were also really, they can also come. Then, like, some questions can be like, so whenever someone teaches, so what they teach, so they teach, they are teaching a particular concept, and based on that you might have also seen that, let's say they, when you were being taught about that high resistance measurement. So based on that you have that volumetric surface, volumetric resistivity and surface resistivity. Based on that, as it is, there was a question on assignments. So if you have read, if you have studied, or if you have listened the lectures properly, then you were able to do that. So that's why there can be, as it is, conceptual based questions being used, concepts being used from the lecture. You can get in the in your exams. Yeah. So just so the question, like some of the topics where you don't find lot of questions in measurement books and all those, and these are very specific to this course only. Okay. So from that there can be a big question, like each and every, you have to like 3 4 questions in sequence, just like that high resistivity measurement thing. Or there was one more thing, or one more question on this one, this coordinate potentiometer and all. Okay, so there also, if you know like how it behaves, so it will not be a problem for you to solve that question. It will take hardly few minutes. But if you know, if you don't know that how it is being done in the lecture session, then you won't be able to do that, because although you know KCL, KVL, all those stuffs, for that, from that you can do this operation amplifier questions and all, but you cannot do like the questions which is like, I will say, which is very specific to what he told you in the lectures. I think you got what I'm saying. You got the point. That is important. Then,
Sir,
yeah,
sir, I have one basic question, sir.
yes,
Uh,
yes.
if uh, uh, if we connect capacitor with the current source, then it is voltage is linearly increasing. But when we connect the voltage source across capacitor, what will happen when suddenly when it is increased? Like so suddenly when switch is closed, sir, what will happen, sir?
Oh, you are saying, like, we have some current source, then we are using a capacitor,
Yes,
like
sir.
this.
It is really increasing. Why, sir? I equal to C into dV by dt.
So
Then,
Q equals to CV, I equals to C dV by dt. So what is happening? Like there should be like we. So your question is like, if we are using the current source, then it is linearly increasing now. You are saying
yes,
that,
sir.
yeah.
But
So, but if you are giving that voltage source like this, then
yes, sir.
it will so let's say what is happening here in this case. Initially, let's say this is a current source, there is this, there is a key here, there is a capacitor, and then we have a voltage source, there is a key here, and we have a capacitor. Let's see what is happening. So when we just put this key on, that is a current source being fed to that. So what is the change in I? Change in I is delta I, let's say. Okay, in some time delta t, fine. Then if there here it is like initially the voltage was zero, so from V to if the change is V, that is V in d time. So what is your question exactly?
When a voltage source is connected, what will be the how it will why it is impulse, sir? But because it suddenly cannot oppose because
Uh,
of why it impulse occurs, sir.
okay, so like capacitors have the tendency to like uh, stop this any immediate changes in voltages. Yeah, and inductors are having this to stop their immediate changes in current. So in case of this thing, so let's say if we analyze this stuff, then I knew the explanation for this. Just wait, let me think. So this is QCDB. We can do, let's say, if you are talking about the delta impulse, let's say there was this V equal to some delta t. Hmm. Yes, okay, got it. So I equals to C dV by dt, and I dt if we integrate, and if we are integrating C dV, then this will be Q. So this is the charge being retained on that capacitor, and this is C dV. Now, if this the change in this is like it's I will say it's impulse, okay, or I can say this. So it's like basically for a very short time, very short period. So impulse is like this. So this is not delta t. The time is delta t. This is v. This was t. So this time is delta t. Like very small impulse. So what is happening actually? So this I delta t integration c dv I by c if we say okay. So if others have the answer explanation for this, they can also like share or they can be a part of the discussion. They can you can write in chat box.
Actually, what I calculated was Laplace transform SS
Yeah,
cancel, so it will be impulse. Like that, mathematically it was proven, sir. But
yeah,
when
ha. But
what happens actually is that charge, new charge introduced, sir. Otherwise,
yeah. So it's like we say that the capacitor is not able to like discharge that charge like that impulsively. So we say that it is having that retaining property. And if you have seen, if you go in, if you really want to go into the physics of this capacitor, then there is like what is happening inside that dielectric medium. So there is this polarization is happening: negative, 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 then positive, 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 then negative. So like basically the resultant field in some way. So if we go physically, then you can say that they definitely these the dielectric medium electrons in the dielectric medium, this polarize these atoms, they need some time for again to polarize back to some different directions. You're getting my point. So these all are
Yes,
like,
sir.
so it they need some time to go back, like, or to change their direction of net electric field. That's it. That is one of the reason why like this capacitor not able to like discharge that easily, or like they oppose this change, sudden changes. But yeah, mathematically I also remember I did something there. There was some mathematical explanation also. But yeah, it's like physically also we should know what is happening. So this is one of the explanation for that. But I think these are all like basic 12 questions. I think I'll have to revise that. So, but anyway, any questions related to maybe this session or this course? So I will say, like, if you haven't started preparing for exams, so I think it is better to like start with that. For all those who haven't like taken assignments seriously, or like maybe the live sessions, they should rewatch these videos and even the lectures, and then try to solve these questions again and again. Otherwise, in the end, it will be difficult for you to, yeah, take a good exam. And you might be having your own like college or university's exams, so you things will be hectic. So just prepare for the worst. Then only good things will happen. So okay, if you have no doubts, then we can end this session here. And I hope you will be solving the questions sincerely, and let's see if you come up with doubts next session with this related assignments and all, or
Sir,
you can, yeah,
please
yeah.
share mail, sir, because it will be helpful.
Mail what? Uh,
Mail, your mail, so that I can send you some questions.
you can
If
post
you
that in the discussion forum. I have posted there. Like, yeah, it's there only. We can reply. Yeah, we will, yeah. I'll make sure like whatever you ask, we will solve it. No issues. Okay then. Thank you for coming. Then I will end this call. You can leave. Good night. Bye bye.